click all the buttons. So I'm going to finish up. There was just a little bit of the lecture that I didn't get to during Monday's recorded lecture. And then, so once I cover that, then we will move into, essentially what I've done is I've just sort of abridged what we would have talked about on Wednesday and today, just into one lecture. That way we're pretty much caught up. Thank you all for being flexible on Wednesday. I apologize for the last minute nature of that. I know that you all are just going through ongoing disruptions and changes, and so sorry to throw another one in there for you. But you know, hopefully on the flip side, it was nice to get a little bit of an unexpected break in class. So like I said, I'm hoping that today I'll have condensed those two lectures well enough that we've hit the highlights and that you're also not feeling overwhelmed. And that way we're sort of back on track to where we need to be. So just finishing up, again, these other theories about attention and how it works. So there was a theory by Treisman and Galade called the feature integration theory. And so according to these researchers, we can use two different types of attention in order to try to process a scene. So we can use what they call distributed attention or focused attention. And so with this idea of distributed attention, it's that this registers features really automatically. And it's so effortless that we're not even aware that we are using it. And so that's also sometimes why it's thought of or described as this pre-attentive processing. So it's happening really outside of our conscious awareness. And it's just second nature. Also, this idea of distributed attention says that this type of attention, it uses what's called parallel processing. And so it's able to then be running different registers of features simultaneously. So then rather than just being like this sort of serial one-to-one of like, oh, there's that object, it's using these really automated processes to be like, oh, those three objects, got it. And so as you can imagine, these are more simple attentive features of stimuli, and it's pretty low level, it's pretty basic. And then in contrast, there's what they called focused attention. And so with focused attention, this does require that ratio of like one-to-one processing, what is called serial processing. And this kind of attention is necessary when the objects that we are perceiving are more complex. So they're not these more simple, basic, automated things, but rather it's when we're encountering these more complex features. It does mean that we have to go slower in our processing as well. And we can also use it to identify which features belong together or should be perceived together. So for example, which shape should be associated with which color, and which combination of those two features we should then be focusing on. And so some evidence for this came out of their research on distributed attention. And so they studied distributed attention using what are called isolated features. So there was a series of studies that they did in which they tested their hypothesis that if distributed attention does exist, then participants should be able to find a target, in this case, a blue X, really quickly among other surrounding irrelevant stimuli. So red X's and O's. And so this should not be only rapid identification, but the target should also seem to sort of pop out of the display, no matter how crowded the target is by other irrelevant stimuli. And so here, this example, you know, if we're looking for a blue X, the feature of the blue and the X combined, they really stand out against everything else that is red, even the red X's. The blue really pops out at us. And so through their study, they were able to confirm this hypothesis. Participants were just as easily able to identify a blue X when the X was really crowded with other stimuli. So they found like with even 23 stimuli, just like filling out the page, that X still popped out, versus when there were like only 3 items on the page. And so these results were suggesting this idea that distributed attention is really this automatic process that takes place. And so they also studied focused attention, which is how they came up with their ideas regarding focused attention. And so to do this, then they switched up the stimuli. And so they then tested their participants' ability to decide whether there was a blue X present in a field of blue and red X's and O's. And so this task is more complex because it's involving the integration of these multiple features of the target that they were looking for. So they had to not only look for stimuli that were blue, but they also had to look for stimuli that were X's as well. And so in this kind of situation, the researchers found that as the number of distractors increased, so as the number of irrelevant stimuli were surrounding the targets, decision-making slowed down. It was a lot harder. Participants had to really slow down and more intentionally look to see whether a target had both blue and an X shape to it or not. And then so this then suggested the idea that focused attention is really this controlled, effortful, slower process. And so they also went on to talk about this effect called illusory conjunctions. So it's a mouthful, but this is the sort of inappropriate combining of features, or the incorrect combining of features. And this is for example, putting one object's shape together with a nearby object's color. And so a number of studies have shown that, for example, if there's a blue N and a green T, the viewer then actually perceives a blue T. So they're incorrectly blending the different features of these very separate stimuli. And so this finding illustrates to us that our visual system actually breaks a stimulus down into its component parts and then processes those parts just independent of one another. So it takes the stimulus and it starts to abstract or break down its various features. So color, letter, shape, etc. And so sometimes the processing system then has this binding problem because it doesn't put all of the features back together properly. In the case of illusory conjunctions, it's mixed them up. And these illusory conjunctions, they seemed more likely to occur. I think I need to be on the next slide. I sure do. So these illusory conjunctions were a lot more likely to occur when somebody was using distributed attention. And so again, this sort of quick, automated, you're juggling several things at once. But when someone was using more focused attention, that person was more likely to then perceive the object accurately. So then they were able to put together the features of that correctly rather than mixing them up. And so one way to think about this, according to a researcher, is that focused attention it's like a form of glue. It's like you're taking like this glue gun and you're sticking the object shape and color together in ways that you remember, okay, that's right, those two things are associated together, rather than accidentally having them be scattered and then you're thinking, oh yeah, I saw, a blue X or a green T. And so this sort of like theoretical idea of these illusory conjunctions, they don't just occur with visual objects. They can also occur with verbal information. So for instance, participants have been presented with two nonsense words, DAX and K. And then they might conflate that, actually combine those features together and say, oh, the word I heard was day. And so this suggests that these illusory conjunctions can conform to or be shaped by our expectations that we have. And so in the instance of this DAX and K being incorrectly combined to be day, at least that the person recalls, the expectation was that there were going to be real words that were presented instead of nonsense words. So already coming into the situation expecting, oh yes, I'm going to hear real words, you're presented with words that aren't real, and your mind is trying to make sense of that and comes up with a word that actually wasn't presented verbatim, but pieces of it were. And so this idea, it actually, since Treisman and Galade proposed it, it has actually been found to be a little bit more complex than they had sort of originally stated, because researchers have found that participants can search pretty quickly for targets when they've had a lot of practice with it. So they might not do well at first when it's this new stimulus, but over time as they practice, there's this practice effect where they get better at it. And so this then suggests that, well, perhaps, focused attention and divided attention, it's not necessarily this dichotomy of, well, it's either focused attention that we're using or it's divided attention, but really they're on either ends of this spectrum, and we're kind of depending on the situation, if it's something we're more familiar with or not, we might be going back and forth between using them rather than just operating with just one in mind to approach a task. It might be over time that starts to become, it might shift from focused attention to a little bit more of divided attention or distributed attention. Any questions on that? All right. So we're going to kind of shift gears here, because all of these all of these theories about attention, it's all well and good, right, to talk about this in sort of the hypothetical. And yes, there have been experiments that have supported some of these theories. But what do we know about the brain that then might explain how these theories could take place? So what's happening at the brain level, more of the sort of neuroscience, neuronal level, that then speaks to how the mind works, so how these theories of attention are operating in day-to-day life. And so there is this domain of cognitive ability that's called executive function. And so executive function, at its most basic, it's described as the set of these sort of supervising or controlling cognitive operations that oversee a lot of are really more sophisticated, nuanced cognitive abilities. So this includes things like maintaining attention, both in terms of like focusing our attention, but then also being able to shift our attention from one topic to the other or one stimulus to the other. Planning, sequencing, so something like, figuring out, okay, well, first, I need to go to my mailbox, and then I'm going to go to the DC, and then I'm going to go to the library. Being organized, whether that's organizing your physical space or organizing information in your mind so that it's more linear. Problem solving, goal-based behavior, and also emotional control as well. So there's really kind of emerged this idea that there's this like centralized controller, or as one of my supervisors has said in the past, she would talk about our executive functions are like the CEO of our brain. They're really overseeing the whole rest of the hierarchy that's underneath them, right? They're at the top of this, and they're overseeing all of the operations day to day throughout the rest of the company. And so with this centralized controller or the CEO, there is the development of these more automated sort of activities. So these really repeated processes, repeated behaviors that become quote unquote second nature. And this then allows for less involvement, less work for the CEO. So it's kind of like if this goes to show how little I've worked in the corporate world. But, if all of a sudden like the mail room was fully automated, things were being sorted out by machines and things like that, then the CEO didn't have to worry about the mailroom department, as much as he or she may have before, because it's like, oh, okay, it's automated, great, that's being taken care of. I can focus my attention elsewhere. And so there have been a variety of theories that have been proposed about how this central executive calls the shots when it comes to executive function. And one of the most prominent has been this idea of this supervisory attentional system. And so the idea here is that there's a supervisory system that is not only in charge of directing where resources go for attention, but that there are resources that are particularly limited. So it's this idea that, yeah, we don't have like, unlimited all access amount of attention that we can pay, that we can use in our world. It's really limited. And so we have to be mindful with how we distribute out the mental energy and the mental resources to support that attention. And so because of the limited nature of this, it's really this sort of supervisory attentional system is really important to things like planning and decision making, right? Because there's a lot of attention that goes into the forward thinking aspect of that. And also you're having to juggle a lot of different ideas and possibilities in your head. And also in the presence of new or really demanding tasks, this is when this attentional system really comes into play, because again, you have these limited resources. If something is brand new, you're going to have to throw a lot more resources at it in order to figure out how to tackle it. Same thing with a more demanding task, driving versus walking to the kitchen. There's a lot more of a demand on your cognition, and therefore you have to be a lot more selective with how you're doling out attention. And there have also been a variety of research methods that have been used to try to investigate the possible neural network. So the possible ways in which the brain is working that then speak to these various aspects of attention that we've talked about. So again, we've talked about these theories, but what's kind of lying underneath them at more of the brain level. And so I know that this slide is probably a lot. I don't think you will find that I'm not a big fan of the book. I wasn't in charge of choosing it, and if I was, I would have chosen something else. And so I didn't think it did a very good job in talking about this one aspect of research. So kind of threw my own thing together. So we're gonna walk through this. So I know that this probably feels like a lot of information, and you're like, oh my gosh, there's like a graph with different colors and like polarity, what's happening? But we're gonna go through that. And so one of the most popular methods has been the study of the timing of when our attentional processes, happen, when they occur, and then connecting them to different brain areas via what are called these event-related potentials. And so these potentials, they're these really small electrical patterns that are generated in the brain in response to specific events or stimuli, and they can be narrowed down to specific parts of the brain as well. And they are detected and recorded during an EEG. So it's great that you can run the EEG, which is the electroencephalogram, that's a mouthful, EEG. And so as you are measuring these more global brain waves throughout the brain, you're also getting these little segments that are essentially these time markers or time stamps of unique electrical activity that signify when a sensory or a motor or a cognitive event is taking place. And so in this way, we can then use them to study when, quote unquote, a person responds to a stimulus. And we can then sort of abstract from there, okay, well, this is where this aspect of attention started happening. This is where this other aspect of attention started happening. And so there are some specific parts of these ERPs that have been linked to certain cognitive processes or responses in attention. And so there are these different waves, and they're named according to whether it resulted in what's called negative polarity. So this sort of dip below the zero here. And these are called N waves for negative, clever. Or there are also waves that are called positive polarity waves. They're these spikes above the zero. And these are called P waves. And so I'm just going to go through just real quick sort of the different electrical patterns that occur as people have been, shown a stimulus and asked to attend to certain parts of it. So at the very, very beginning of this measurement, so right here where we don't have any dips or spikes, but we do have a little bit of activity here, this color before this black line, this black vertical line. In this period of time, it's about 100 milliseconds. So it's really quick. And this part is associated with sensory processing that's happening. So this is the part where the sensory input is online and it's being taken into the brain from whatever sensory system of the body, taste, smell, whatever the case might be. And then the waves that happen after this portion, we know that they're no longer involved in sensation. So the things that happen after 100 milliseconds, we know that is when perception and more higher cognitive processes are coming online, such as attention. And so we have these waves, they're called N100 or P100, meaning that they're happening around the 100 millisecond timestamp, and then either positive or negative, again, very cleverly named. And so these waves have been associated with selective attention. And so instances in which you are having to shift your attention to a particular stimulus in the midst of other stimuli. This is when that's taking place. And these are the kinds of brain patterns that are happening during that time. And then at about the 200 millisecond mark, we have a wave that shows up when a stimulus is really physically incongruent. So when there's this sort of mismatch between what you have experienced before and what you're currently experiencing. And so this, for example, like if a G note was played on a piano after a series of C notes, suddenly you're realizing, oh, wait, that was different. The amplitude of that note, that frequency was different than the other ones that I've heard. The P300 wave or P3 wave, this is sort of described as a sign of like readiness. So just sort of this basic attention where you're not attending to a particular stimulus per se, but you're ready. You're ready for something to come at you. And then the last one that I'll talk about real quick is just this one called N400. And so this takes place when there's a change in meaning to the stimulus. So all of a sudden you get thrown a nonsense word, and it's like, oh wait, this is a change in meaning. And so again, these are some different wave patterns that we see that we can connect to different aspects of attention and also give us different markers. So just being able to trace the temporal like progression of cognitive processes. So there's this classic study in the 70s by Hilliard, Hink, Schwent, and Picton. I'm always afraid that I'm getting these last names wrong, and I know that I am. And so again, this was one of the studies that put on the map this idea that certain wave patterns are connected with the attentional focus and also detecting a stimulus in the field. And then this actually supported Donald Broadbent's filter theory because, as you might remember, we saw this brain activity that was already online during the sensory portion of things. And so some of this then sort of enhanced attention, sort of set you up to pay attention to certain things really early on in the attention process. And so this change, this beginning shift in attention is really happening really early on in the information processing period before these sort of other attentional mechanisms start to operate. And so this then gave this more abstract filter theory that was like an early theory of attention, some like neurophysiological proof. It was like, hey, yeah, there is some evidence to this in the brain that these attentional components are coming online earlier than we think. And so things are happening before they even reach this attentional filter that is proposed to exist. And so research with a variety of methods, so these event-related potentials we just talked about, fMRIs, which if you'll remember, This is a way to track brain activity based on the uptake of oxygen in the brain, and also some brain damage cases that we'll talk about in a little bit. But research in these various modalities have shown us that attention, it takes place across many structures in the brain. So there's not just one structure or region that is like the attention central. And like I said, we've learned a lot about the specific role of different areas, also through brain damage cases as well, that we'll talk about. And so this slide, I know this is a lot. You will not have to memorize this for the test. There will be some of these brain areas that I'll be talking about later in the lecture, but I'm just going to keep it really surface level and just really talk about the gist of what they do. I put this graph in here from a really great neuropsychology textbook I have, just to show you all of the different areas that are involved in attention. And if you have taken a neuroscience class or familiar with brain neuroanatomy, you'll also realize that these are areas that are scattered all throughout the brain. So again, they're not concentrated. They're all spread out all over the place. And so, like I said, there are these widespread projections throughout the brain, and they involve a number of regions. So the upper brainstem, the thalamus, the hypothalamus, the basal forebrain, and the frontal and parietal lobes, which, as you might remember, the frontal is straightforward. It's right here in the front. The parietal are the lobes that are more towards the top of the brain. And so I don't want you to get bogged down necessarily in like, oh, okay, the upper brainstem is involved in attention in comparison to the lower brainstem. But again, I just point this out that just to show there are a lot of different areas involved in attention. And so specifically, a lot of research and a lot of information has been talked about the frontal lobe and its role in attention. And so because executive functions are said to reside within the frontal lobes, and this is because so much activity takes place here that's associated with executive functions. And like we talked about, executive function has a lot to do with our initiation of our attention, deployment of our attention, sustaining our attention, shifting our attention. And so within the frontal lobe, there are two areas that are especially crucial to attention. So there's one area called the prefrontal cortex, and this plays a role in a number of attentional aspects. So things like sustaining our attention, reducing our distractibility, reorienting our attention to relevant stimuli. So when you're like, oh, okay, I got to get back to reading. I know I just got distracted by that squirrel that's outside. And I say that because I was just distracted by a squirrel that's outside. So it's relevant, it happens in real life. So my prefrontal cortex then helped me reorient my attention to the relevant stimuli of this lecture. And also helps direct our eye movements, and that's in conjunction with some other structures we'll talk about briefly. And then another part of the brain that's near the frontal lobe, it's called the cingulate cortex. And so this part of the brain, it has really rich connections with the limbic system. Does anybody remember kind of what the primary purpose of the limbic system is?
Isn't it responsible for like emotion and motivation and hormones?
Yeah, absolutely. You know, really boiled down to its most simplistic, the limbic system is in charge of our emotions. And so, great, Julia. And so because of these connections between this part of the brain that's involved in attention and emotions, it's really involved in the integration of our emotions with with our attention. Um, and particularly, there is the anterior or the forward facing part of the cingulate cortex that's involved in the sort of what we call these motivational aspects of attention. So, like Julia touched on, this involves essentially how we we go about deciding whether something is like a relevant or interesting stimulus, and then directing and sustaining our attention to that. So this is the part that says, oh, hey, this is important. I should pay attention to this. Or, oh, hey, this is no longer important. This is actually more important. And so it's what sort of helps pinpoint that and helps us sort of assign this like meaning or value to a stimulus and then attending to it. And so, as you can imagine, the frontal cortex and the cingulate cortex, they work together along with all these other widespread areas in the brain to direct, inhibit, sustain, and shift our attention. So it's really this idea of like this teamwork approach. So a lot of what we've been talking about so far in the models of attention have mostly come from research on auditory attention. There has been some talk of visual attention prior to this as well. But now we're really going to talk about visual attention and sort of hone in on what's happening in the brain in terms of its structures and pathways when we are visually attending to something. So there's this metaphor that has been developed called the spotlight metaphor. And this has been proposed as a way to help us really talk about and understand our visual attention. Because our visual attention, it can be focused on objects within our visual field, like a spotlight, while the rest of the visual information that doesn't really have that spotlight of attention, it just becomes unattended. Which this really means that it's not that we're not seeing it. It's not that, oh, okay, I'm just focusing on this PowerPoint and everything else behind it in my visual field is black. But really, we're seeing the rest of the information that's outside of the spotlight, but we're not really processing that information as much in comparison to what's being focused on. So, for example, if you are asked to describe what somebody looks like that you just saw pass by you on the street or on campus or something, you know, you're probably likely to focus on certain aspects of that person of like, oh, their eye color, they had blue eyes, their race, their height, their hair color, over some other things that you saw as they walked by, like the color of their shoes, despite the fact that you did see their shoes, but that's not what your visual spotlight of attention was focused on as you saw that person. And so you saw it, but you weren't processing it. Therefore, it's a lot harder for you to recall versus, okay, well, what was the, you know, hair color of this person? And so there's a cognitive researcher named Michael Posner, and he developed an experimental method that he used to test out this spotlight metaphor idea and try to get a little bit more understanding about it. And so it's called the flanking task. Another critique of the book. I promise I'll get off my book soapbox eventually. But I know that the book talks about this as being a covert attentional task, but I don't think it does a very good job of defining what that means. So just to sort of help differentiate, covert attention is our ability to pay attention to part of our visual field without moving our eyes. So covert attention is what allows you to sort of see what is in your periphery. I'm able to see my finger moving around even though I'm staring straight ahead. Anyway, that is an aside. Hopefully that makes the chapter reading a little bit more clear. And so anyway, in this experiment that Michael Posner conducted, what he did was he asked his research subjects to pay attention to a stimulus in a fixed or in a particular location on either side of this this fixation point. So essentially, he told them, you know, you're gonna focus your eyes here. It's typically a cross or an X, but it can be a dot as well. And then they were going to be shown stimuli that were flanking, so on either side of that fixation point. And so then the participant is then asked to indicate whether the target then appeared on the right or the left side of the fixation point. And they do this by just clicking a corresponding button. So, you know, maybe on the keyboard, it's like push, I don't know, M for right and Z for left, or whatever the case might be. And so the flanker task allows for the testing of both voluntary and non-voluntary attention. And it does this by giving subjects either correct or incorrect information about what side or flank the target is going to appear on. So I'm going to explain this a little bit more, and then we're going to watch a video that hopefully will better describe it. So in the short video that we're going to watch that demonstrates this experiment, the participant is given a cue about which side the target, in this case is going to be a black box, will appear on. So the cue is going to be in the form of, it's just an outline of a box. And then the stimulus that participants would be responding to and saying which side it appeared on is this black box. But the cueing information isn't always accurate. And so in Posner's study and in subsequent flanking tasks, this cue was accurate 80% of the time. So 80% of the time, the cue was on the right side. That also meant that the target was going to appear on the right side. But this meant that 20% of the time, the black box then appeared on the opposite side of the given cue for the trial. So let's go ahead and watch this short video that I hope will better understand how this works, and then we'll talk a little bit more about what the flanking test then tells us about concentration. Also, you're not hearing any sound because there isn't any sound on this, so FYI. So that was an example of an incorrect cue. There was another incorrect cue, right? We were shown a cue, and then the target, the black box, showed up on the other side. Whereas that was a example of a correct cue, where the box shows up, and then the black square shows up. That's correct. And so again, participants are given the correct cue about 80% of the time, and then the remaining 20, they're given the incorrect cue. So they're given the wrong information about which side the black box is going to appear on. Okay, so as you could see in that video, then this arrangement of correct and incorrect cues can be varied from trial to trial. And so by mixing them, Posner was able to then find a difference between the reaction times on trials with the correct cues versus the trials with incorrect cues. And he found that participants responded more quickly when the cues were correct. So when they said, oh, it's going to be on the left side. Oh, it's on the left side. They responded faster than when the cue said, it's going to be on the left side. Just kidding, it's on the right side. And this suggested then this faster response time in the presence of correct cues suggested that there's this anticipatory nature of our attentional spotlight. And that with correct cues, we are more efficient and we're saving time with directing our visual attention. And some researchers in 1991, Hilliard and Mangun, they used this Posner flanking task and then they paired it with an EEG so that they could record the event-related potential. And so their results showed that participant expectancy, or that readiness, that P300 wave that occurred at certain time intervals, it altered the sensitivity for the regions of space in which the targets were likely to appear. So essentially, this is some neurophysiological evidence that certain cues in our environment predispose our visual attentional system. So when we are given cues, we then are ready for a particular stimulus. And this then allows us to try to focus our attention like a spotlight. And so now, so in addition to these like theoretical models and experiments, now we're going to talk about the evidence that we've gotten for how attention works from people in which attention no longer works. So people who have sustained brain damage in some way that disrupts their attentional capabilities. And so we've learned a lot about visual attention from cases of people with what's called visual neglect. And so this is this inability to sort of pay attention to one half of your visual field. And this neglect usually occurs after unilateral or one-sided damage in the right hemisphere. And it's particularly when the damage is in the right parietal lobe. And the parietal lobe, as you might remember, it's really crucial for perception and also association. So being able to integrate all the visual information that we have coming in. And again, remember that because the brain is set up so that the incoming information is sent to the contralateral or the opposite side, this means that damage to the right parietal lobe leads to neglect of the left side of the visual field. And so Posner and colleagues in '84, they investigated how left and right brain damaged individuals were able to navigate that Posner flanking task. And so they found that if these participants were given a correct cue in the neglected side of their vision, so again, the side of vision that was opposite where the damage was in their brain, they were then able to respond in about the same amount of time as those without brain damage. And so this suggested that they were able to be directed to pay attention to the side of their vision that they typically neglect. So in those with right-sided damage, for example, you know, in the left hemisphere, once there was a cue there, it directed their attention. So they are no longer neglecting that side of their vision. They were then attending to that side of their vision because of this cue, this external reminder of, hey, you look over here. However, in the cases in which the cues were incorrect, so these participants saw a cue telling them, hey, the target's going to be over here on the left side, and then it was actually shown on the right side. The patients with visual neglect, they weren't able to pull their attention away from the side where they had been given the cue. They weren't able to go, oh, well, it said left, but actually it's over here on the right now. They weren't able to redirect it to the correct location. So it's kind of like they were stuck because of that cue. So they're not paying attention. You give them a cue, and that's what they then pay attention to. They're then not able to shift their attention to the opposite visual field, which again, if it's in a right-sided damaged patient, if they're given a cue in the left field, they're not paying attention to that field generally, but suddenly they get this cue, they go, oh yeah, that's right, I should look over here. But then when the target goes over into the side of the vision that they normally pay attention to, they're not able to redirect or reorient their attention over to that target and respond accurately. And in comparing the left and right sided individuals, there were people with the right sided damage, they just had more difficulty with this flanking task overall. And this was suggesting that there's a greater role of the right hemisphere when it comes to our visual spatial attention. Gonna do another critique of the book because with the addition of information that has come from studies that have been looking at brain damage and its impact on attention, there have been proposed models about the kinds of neural networks that are involved in the attentional processes. The book is a bit outdated when it comes to what we know about attention. It said, well, there's some emerging research. So I wanted to give you some more updated research. Again, this is a lot more cognitive neuroscience-y. So I'm just going to really try to hit the highlights and not get us too bogged down in the particulars of what's going on in the brain, but just to kind of try to give you a general overview. And so current models of attentional control, they suggest that there are these two separate frontal parietal, which is just a fancy word for involving the frontal lobes and the parietal lobes. Shocking, I know. Yeah, so there are these two systems that are operating within the frontal and parietal lobes. And so one, we have the dorsal attention network or system. And so this is primarily concerned with our spatial attention. So paying attention to the 3D world around us, right? Versus the ventral attention system, which is a separate set of neurons. And this is concerned with non-spatial aspects of attention. So this is more object-based. So like feature detection of objects, object identification, things like that. And interestingly enough, the ventral attention system is mostly in the right side of the brain. We found evidence for that. There are also some subcortical attentional control networks, which really means just deeper in the brain. There is the superior colliculi, which is one of my favorite neuroscience words. I love saying medulla oblongata and superior colliculi. It's great. That's a fun little just like neuroscience nerd moment. But anyway, the superior colliculi, which are further back in the brain, they are involved with directing our eye movements and also conducting visual searches. So like if you're looking for your friend in a crowd, your superior colliculi are on it. There's also a portion of the thalamus called the pulvinar, which is fun. And so this is really involved in our selection for color, motion, or orientation. So if you were told to pick out a blue X, right? Suddenly you're well, not suddenly, but your pulvinar region of the thalamus is like, okay, blue, 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 blue. So in addition to like our three-dimensional space, like I alluded to with this ventral attention system, so we also attend to objects as well, and the specifics of objects in our environment. And there is this condition called balance syndrome, in which it's a breakdown in our ability to attend and be aware of our visual, what's going on in our visual field. So it's caused by bilateral damage to regions of the back part of the parietal lobe, and then the occipital cortex, which again we know is very involved in perception, and the occipital lobe is involved in vision. So as a result, somebody has a difficult time with um, seeing like more than one object, or even sometimes even being able to perceive more than just a small portion of an object. So if you simultaneously present them with two objects, they're not going to be able to differentiate, oh, that's item A and that's item B. They can only just see one or one part of it. This also leads to left-sided neglect and difficulty with shifting their visual attention. I have a short video that I will show you real quick of somebody with balance syndrome being asked to identify some objects. Okay, need to share my sound. Okay, I'm going to jump ahead. He's just seeing if he can see just the spoon, and I want to get us to the part where he then is showing him a couple of different objects.
Exposure to it, like.
Can everyone hear the sound? Well, there's no sound right now, so that's
a comb.
Mm-hmm.
So showing him a comb.
What do you see now?
And now a spoon.
Comb.
What do you see now?
Spoon.
Do you see the comb?
No.
Do you see the comb?
Yeah.
Do you see the spoon?
Mm-hmm.
Now he's not able to
What do you
perceive
see
these
now?
two objects.
I see the spoon.
What do you see now?
Comb.
Do you see a spoon at all?
No.
Okay. Can you see what? Just tell me what you see.
Experimenters moving the spoon around, trying to see if the movement gets his attention and gets him to be able to perceive that object. He's only able to see either the comb or the spoon. He can't see them simultaneously. And so that is an example of somebody with balance syndrome. And then finally, we have cases of people who have neglect of both objects and space that happen simultaneously. So there's a study by Berman and Tipper so that found that the neglect of an object kind of followed that object even when it was moved to the side of the vision that somebody usually sees. So again, this neglect of not only certain space in your visual field, but then the objects that are there as well. And then finally, there's this really interesting study that came out of Italy that has to do with instances of people who have neglect of even imagined space. And so these researchers, they studied participants with neglect that had been caused by damage to the right hemisphere. And they asked the patients who were from Milan in Italy to imagine themselves standing on the steps of the Milan Cathedral. So the Duomo di Milano, clearly I don't speak Italian. And to describe what the piazza, the church square looked like from memory. So just to give you a frame of reference, right? This really, really beautiful, detailed space, very wide. And so they're asked to, in their memory, face a certain point in this church square outside of the cathedral and to describe what they were seeing. And so interestingly enough, the patients who neglected things that were contralateral to the piazza, so let's say, for example, they were damaged in the right side, couldn't see on the left side, and the piazza was on the right side. So they were then describing what they saw, and they weren't talking about the things that were on their neglected side. And then if they had them turn around and face the other direction in their imagination, they then reported items from their memory that they had just previously neglected. And then they neglected the other side of that sort of visual scene. And so this study suggests that this neglect for items in visual memory happens when people with this condition are recalling a scene, as well as when they're physically present in that scene as well. And so this goes to show that it wasn't like they were lacking memories of this scene, right? If you piece together what they were imagining, you did get this accurate 360 view of this cathedral. But rather, it was attention to the parts of the recalled images that were biased. So it was a problem with attention that then had negative implications for their memory, for their recall. And yeah, so even in their imagination, people who have neglect of one side, they neglect it when they're recalling certain images, depending on which way they're sort of standing in their imagination, in their mind. Does anybody have any questions on the lecture today?
I have a few questions just on the general questions.
Yeah.
For the test, do you want us to remember the names associated with all of the studies? Or just kind of what they were about?
Yeah, more about what they were about. If you aren't able to remember, Bisiach and Luzzati, again, I don't speak Italian, I'm so sorry. That's okay, but if you're able to tell me what happened in this study, right? You're saying, these researchers from Italy, they were studying patients with unilateral neglect due to damage in the right hemisphere, and these were their findings. I care about that a lot more than you being able to tell me, well, these 4 authors in 1973. If you're able to do that, great, but I'm not going to take points off because I don't necessarily, the point of it isn't for you to memorize the researchers, it's for you to understand what they found and what they did, and why it matters, why are we talking about it? Yeah, great
Gotcha,
question.
that helps, thank you. And then the other question I had, kind of related, but is we went over the polarity waves and how different ones are associated with selective attention or whatever. Do you want us to memorize those?
No, I'm not going to ask you
Okay.
the specifics of the waves. There's not going to be a question that's like, what is the N400 wave on an event-related potential? That was more just an illustration to show you of how useful that way of research can be in terms of being able to give us a tag, and the fact that those waves have these specific patterns that we can say, oh, that's an N400 wave, and that tends to occur when XYZ happens. I think the N400 was when there's a change in the meaning of a stimulus, right? And so we can say, okay, that's that part of attention. And I was nuancing that just because, these event-related potentials will come up in some other studies, and you also might encounter them in your research that you're doing as you're working on designing your own study, just because it is such a popular method of study. And I wanted to just make it hopefully a little bit more clear because I don't think that the book does a good job of that. So yeah, I'm not going to test you on the specifics of those. This isn't a cognitive neuroscience class, so you're good to go on those. Yeah, just more conceptually,
Okay, thank
so you
you.
can kind of understand what those are about. Yeah. Does anybody have any questions?